Okay, we're going to be talking about continuity, and we're going to be looking at the calculus definition of continuity, and it's defined in terms of limits. But when we talked about continuity in, suppose, like a college algebra, okay, so let me write that down, in like a college algebra or algebra course, we would talk about the hand-drawn graph. And when we would draw the graph, okay, so let me write that down. When drawing the graph, you don't lift your pencil. All right? So when drawing the graph, you don't lift your pencil. That's what it means. That's what it meant back then. You draw the graph. It's continuous if when you're drawing the graph, you don't have to lift your pencil. So for example, say that this is the curve. Notice I didn't lift my pencil. But if, say, this is the curve, and I lifted my pencil to continue it this way because it's got this kind of asymptote there, well, it's not continuous clearly right about here because I had to lift my pencil to continue drawing the graph. So that's what we said back in the day in college algebra. Now we're going to take a look at it from the calculus perspective. Okay, so this is the calculus definition, if you will. And it's defined, continuity is defined in terms of limits. So it says, let C be a real number on the x-axis. It says the function f is continuous at C if the limit as x approaches C of f of x equals f of C. What does this mean? This means, algebraically anyway, you could plug in, okay? You could plug in C right away and you get the limit, okay? But in the event that you can't plug it in, all right, which if you can't plug it in, there's a hint there that it's probably not continuous. But you can also verify by looking at the graph, and so long as at that point C you don't lift your pencil to draw it or to trace it, I suppose, then it's continuous. Otherwise it's not continuous, it's discontinuous. Now in calculus we also talk about right continuity and left continuity. And so what do we mean by that? Well, this is why we talked before previously about one-sided limits. So if you're looking at it from the right, if you're coming in towards the function from the right, okay, you should be able to plug in C and you get that particular value. The same thing happens when you go from the left. You should be able to plug in C and get the value on the left. Okay, so in order for it to be continuous, all right, number one, we must have a limit that exists. Okay, because this right here implies that the limit exists at C. So I'm going to write that down. Limit exists at x equals C. And what do we know about limit existence? So for a limit to exist, all right, then the left-hand side has to equal the right-hand side limit. Okay, that's just a little note on limit existence. So that brings us down to what we call the continuity test. And look at what I just said. Okay, f of C has to exist, the limit has to exist, and they must be equal. That means that you need to be able to plug it in and get the limit. Okay, it has to be that case for it to be continuous. Well, what do we know is always continuous? A polynomial. That's why polynomials, if you recall in a previous theorem, I believe it was theorem 2, polynomials, to find a limit of a polynomial, you just plug in. That's because polynomials are continuous everywhere. That's a special reason about a polynomial. So we've got some understanding about continuity. We talked about the college algebra definition that we've learned before. We talked about the calculus definition with limits. Now let's apply what we just learned and solve some problems here. Okay, so find all the points on number 1 where the function is discontinuous. So I'm going to point out that I've got 2 holes on the graph. Okay, they're jumps. All right, so when I trace this graph at those 2 points, -2 and 2, I've got those holes, and so my graph is discontinuous there. And then the other thing that I'm noticing is that at 0, I have this asymptote. So to answer this question here, where is it discontinuous? Well, we're going to say at -2, at 0, and at 2. Those are the 3 points rather where it's discontinuous. So that answers that question. All right. Now, looking at number 2. All right. I'm going to pretend for a second that this graph is not there, and we're going to do this problem twice, and we're going to verify it. So let's pretend the graph is not there. All right. I'm going to erase that red X, but I want to point out something. If I were to draw a number line, and I'm looking for the limit as x approaches -1, so I'm going to put -1 right here on my number line. All right. They want the limit from the right-hand side of -1. So where's the right-hand side of -1? Somewhere right in this region. So what numbers are to the right of -1? That means numbers that are bigger than -1. So where would I go on my set of piecewise defined functions? Okay, so let's see here. If I plug in -1, where would it go? Well, let's eliminate the obvious, okay? We know -1 is not between 3 and 5, so it can't be this one. We know -1 is not between 1 and 3, so it cannot be this one. We know -1 is not equal to 1, so it cannot be this one. We know -1 is not between 0 and 1. It cannot be this one. Is -1 between -1 and 0? For sure, especially because it has a less than or equal to. The equal to means that we include it. It is inclusive. So what I'm going to do to figure this out is I'm going to plug it in. And I'm going to say the limit as x approaches -1 from the right of f of x is equal to negative of -1 square plus 1. And let's figure that out. That is 1 times a negative plus 1. That's 0. So my answer here is that it is 0. All right, there's my answer. That's the answer to the limit, okay, that it's 0. Now, we have the luxury here in this case, but you don't always have the luxury of the graph, but we have the luxury of the graph. So let's go ahead and take a look at -1, and we're coming in from the right. So here's -1, and I'm coming in to -1 from the right. What is my y value there? My y value there is 0. Okay, so there's my limit. So then the same thing is verified here, that it is 0. But I'm going to point out an interesting thing. What happens when I approach -1 from the left? Well, the graph doesn't even exist to the left of -1. So the left-hand limit at -1 actually does not exist. So that is very important to note when you're looking at this problem. Okay? So we're going to take a look at one more example to go along with this. All right. And let me pull it up here. It's this one right here, number 3. Okay. So what are we asking? It says, to what new value should f of 1 be changed to remove the discontinuity? So what do they mean? Okay. Well, let's just assume that we have the graph and it looks something like this. Okay, and this is the value when x equals 1. All right, I'm just pretending this is the graph. I don't know if that's actually the case. All right, but clearly it's discontinuous at 1, and let's see why. All right, what happens when we verify the value at to the left of 1. So we're going to again consider a number line. I'll write it over here. All right, we're going to consider a number line 1. I'm going to plug in 1 here, all right, on to the left of 1, because this one is to the left. This one is to the right, okay, because it's greater than 1. Right, left, okay. Now I'm going to plug in the 1. So I'm going to say, okay, on the left, I have 1 square plus 2, which is 1 plus 2, which is 3. So the limit here is 3. All right. Now let's verify the right-hand limit. Again, these are limits, okay? So we're checking the limit, and let me write that down here at the bottom, just so you know we're still talking about limits and not necessarily plugging in. X approaches 1 from the left of f of x equals 3, and the limit as x approaches 1 from the right of f of x, and we're going to figure that one out right now. So we have x plus 2, so we're going to say 1 plus 2, and that is also 3, so this limit is 3. So the limit on the right is 3. But notice what they say. At 1, at x equals 1, the y value is 1, okay? The y value is 1. All right, so what is the question again? It says, to what new value should f of 1 be changed to remove the discontinuity? So what they're saying here is that there's the graph, and let's say that this is the y value 1. Well, it's got this little point down here at the bottom where it's actually defined. So what happens? Well, we would need to shade in this circle, and that means that this is no longer needed, and we would have to change y to 3. So to what new value should f of 1 be changed? To 3. F of 1 would need to equal 3 to make the function continuous. All right, so that's what we're getting at here. All right, so we verify continuity really in calculus with limits. In the college algebra class, we don't talk about limits, but there's the underlying concept, is that we're really talking about a limit when we talk about, well, your graph, when you draw the graph with your pencil, you don't lift your pencil. Okay, so we don't really get into that discussion, that deep of a discussion, but now we are. Okay, and now we understand the reasoning behind it. So, as always, if this video is helpful, be sure to like and subscribe.